So, welcome back to my YouTube channel where I make stuff that I think is fun. So today, I feel like analysing applied stochastic processes. These notes were originally written by Sam Aliska Taylor, and this is more of a criticism and analysis of the stuff that he's written as opposed to me stealing his notes and rewriting them. Then again, I stole his notes and rewrote them, but that's because that's how you're supposed to revise when you're at university, right? And I want to give my take on some of the stuff that's been taught and some of the interesting concepts and some little insights that I've made whilst I've studied the first 24 pages. So, and maybe some solutions to interesting exercises. So, without further ado, let's get on with it. The notes actually end up starting with a preliminary section here, which I thought was nice to reread over, being that I had all but forgotten most of stochastic processes in second year. I think it went by ST202 at the time. This module, of course, goes by ST333 or ST406 for the fourth year modules. Well, for those doing the fourth year content too. But as someone that's only doing ST333, I'm probably only going to eventually fully analyze all of these notes by virtue of just the third year content. So, what's the main difference between stochastic processes in second year and stochastic processes in third year is this notion of continuous time Markov chains. So the preliminaries actually discuss some of the basics of discrete time Markov chains, which are actually much easier to play around with, but give a very nice intuition for continuous time Markov chains. So going over the preliminaries, I'm just going to quickly pull them up real quick. It starts off real simple. As you can see, I've got the notes sort of like parallel here, my notes and the notes there. Yeah, so the Markov property just basically means when you have a Markov chain, when you're trying to move to the next state, which is basically what this bit is saying. So it's saying, say I know the state currently like is here, and I'm trying to move to this next state, I sub n, then the whole probability of this happening is wholly independent of the past. So I can sort of eradicate this bit, and I end up getting just the same probability, which is sort of like forgetting everything that happened. So I wrote down here, the chances of you moving to some other state is independent of your history. I think that's nice and easy to explain it. Moving on. So there's time, is that right? Time homogeneity. So yes, okay, seems like I wrote that here as well. I wrote down that this is the chances of how you jump between states is independent of the time you do it. So basically, what it's saying here is, this is just some notation that means probability. If you ever see this, this just means the given the event x naught equals I. So here I'm just saying, assuming I start at state. Where am I here? Yeah, assuming I start at state I, and I go to state j in one step, I will denote this as that probability. Actually, yes, here, look, I've stated this definition actually right here. What am I doing? I'm being silly. It says the time homogeneous matrix of conditional probabilities, blah blah blah, is called the transition matrix. Okay. And we say that the probabilities are time homogeneous if you do not depend on n, i.e. I can basically reduce this down to the same probability as this. The matrix basically just tells you all the different ways of being able to jump between two states. So what does that really mean? It means that if I'm trying to, maybe my states kind of look like this, okay? This really just means if I'm at state 1, 2, 3, so each of the rows corresponds to where I currently am. 1, 2, 3, 4. The probability of me moving from state 1 to state 1 is 1. The probability of me moving from state 2 to state 2 is 1/3, and state 2 to state 1 is 1/6. State 2 to 4 is 0. Probability of moving from state 2 to 3 is 1/2. So what you could do is probably diagrammatize this like this. 1. So the chances of me going back to 1 is 1. The chances of me going from 2 to 1. So let's say it's like this. 2 to 1 is a sixth. The probability of moving from 2 to 2 is a third. The probability of me moving from 2 to 3, so let's say 3 is here, is 1/2. Okay. And notice all of the probabilities end up summing up to 1, because what you're trying to say is you're trying to describe every single possible way of moving out from 2. And hopefully the probability of you moving out or wherever you're going to move, the chances of you moving anywhere in the future is always supposed to be 100%. These sort of Markov chain things, these stochastic processes, they're sort of infinite ideas where you can keep going on and on forever. So you'd hope that the chances of you leaving and going somewhere in the next time step, which is what these ends represent, the ends are like time steps, is going to be 1 if you add up all of the probabilities of leaving. So that is all of these arrows pointing away here. The probabilities sum up to 1. You can see that here actually with 1, because the only arrow that moves out from 1 is this one, and it has probability 1. In the case of the matrix, it just means row sums are 1. So let's finish off this diagram. It might be more illustrative to denote it like that. So here I'm going from 3 to 2 by probability 1/6. I'm going from 3 to 3 with probability 1/3. And I'm going from 3 to 4 with probability 1/2. So let's say it's 1/2 there. And state 4 goes to 4 with probability 1. Okay. Whoops. Probability 1. Okay, so you can kind of use this ugly-ass diagram here on the left, actually, to illustrate this entire, process. It's sort of like a random sort of walk, where each stage is sort of flipping a coin, and the coins, maybe they're four-sided coins somehow, and given that, it tells you how to jump forward. I think these things are really quite straightforward, because all it is a matrix of just probabilities that tell you how to jump from, 2 to 3, 4 to 4, and so on. Notice, I think I don't know if I mentioned this here, but I thought it would be more convenient if they mentioned how these stochastic matrices are always supposed to be square, because they're supposed to represent jumping between the two state spaces, between elements in the state spaces, which means that if you're using all of the rows to represent where you're currently starting, it should correspond, there should be as many columns corresponding to where you end up, because you're not changing if you're going from state 1 to 4 to state 1 to 5. You're keeping the total number of states constant. So I thought it would have been more clear if they mentioned that, but it's sort of implied. I think some of the notation, was it here where some of the notation was a bit annoying? No, not really. Let's see. Okay. Okay, I think the notation here was okay. It's much easier to read, but it should have been probably mentioned that this was some sort of square matrix with certain dimensions. It is implied by the idea that I and J are in I, but you kind of need to notice it, and that's something you would notice in second year. At one point, you probably have done an exercise that says that, but you never know what you forget. Okay, next thing we ended up discussing was these stopping times, and stopping times I thought were, they're these concepts that are really straightforward in second year, but you need something to refresh us. So it's really nice that I went over it. All it really means is that the time event, so it sort of literally behaves like a time, but it says that it only depends on the history up until then. So usually what these Markov chains things do is they sort of are like, hey, I forget about my past, right? The probability of me moving from my state to the next one is independent of any of the other history, which is really what we meant by the Markov property. What the random time being a stopping time thing does is it says that the event t is less than or equal to t, so the chances of the time being at most something is wholly dependent on the history up until that time of my Markov chain. Okay, well, my stochastic process, but in this case we're going to say Markov chain because most things here are Markov chains. I thought it was a bit annoying that he switches between t and n quite regularly. So here it's assumed that this is a continuous stochastic process, but we haven't quite really mentioned exactly what a stochastic process is. Have they mentioned it here? I remember they sort of mentioned offhandedly at the beginning of stochastic processes in second year that it's just a continuous random. No, it's just a set or a family of random variables indexed by something. Here they just assume that you know that, and they assume that you can do it where it could be continuous. So here I can have x of 0.001 or something like that. Whereas in first year, you would probably only see objects like this, or x of 0 as well. Whatever. It's something to think about, but it shouldn't really ruin your understanding. The strong Markov property basically says that Markov properties... Okay, well, here what I said was if you randomly hop on a Markov chain at finite time, on finite time only, depending... without thinking about the future, the Markov chain behaves like the exact same Markov chain as usual. So I think what I meant by this was, what they say is conditional on the idea that the stopping time. So suppose you're given a stopping time, and you know the stopping time is finite, okay, and at that stopping time, you're at state I. Then in the future, so x of t plus t, it's a time homogeneous Markov chain with blah 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 transition matrix. So if you keep the same transition matrix, it basically says that the way you jump between states stays the same. So what I'm really saying here is that I'm basically behaving as the same Markov chain as before, with the initial distribution basically saying I start yes at x of t equals I. So that's what this bit basically says. It says, yes, I'm forced to be x of t equals I, and then this is the same time homogeneous Markov chain. So I don't really care about how the Markov chain behaves with respect to time. I'm just assuming whatever happens at... what really matters is the difference in time. That would affect my Markov chain. So if I'm thinking maybe 3 seconds in the future, that's really the only difference, as opposed to if it was at time t equals 6 and time t equals 9, which is still 3 seconds in the future. Okay, a stochastic matrix is a matrix that does all of this shit. Okay, really all it is this matrix that I was on about before. It just represents all of the states and the ways of jumping between them. So non-negative entries and the row sums are 1, implicitly square if finite I. So yes, I is only assumed to be countable, which means that you can have something like an infinite matrix, maybe something like, it looks kind of like, I don't know, ... Or actually you could just imagine this one here, where you kind of get rid of this, ... and then say, I don't know, zeros here, zeros here, and more states here, where this isn't 1, 2, 3, 4, and then sort of the same thing on top. So yeah, you could have something like an infinite matrix, but I'm not sure how well defined an infinite matrix is per se. All I understand is ordering elements in this manner is actually well defined. I see no issue with it. All it's saying is, yes, you can list off a bunch of elements that do these sort of things, and they're indexed by I and j, which are 2 countable objects. And I am a strong believer in axiom of choice. So I believe that the cross of 2... Actually, never mind, it's a finite crossing of countable sets. Because I is countable and you're crossing it really to index all of these pij's. So it's sort of like... Yeah, no, it's still countable because z cross z is... So is z Cartesian product. When I say cross, I mean Cartesian product. Z Cartesian product with z is still a countable set. You can look that up, it's just some set theory. Yeah, so one can read off the Markov chain from its transition matrix. All transition matrices are obviously stochastic matrices. Easy peasy lemon squeezy. The Chapman-Kolmogorov equations are basically just this thing that say, hey, this is just one way of being able to jump. Well, say I know how I start, then I can, at the nth time frame... Why did I write x to the n? I meant x sub n here. Let's fix that. Yeah, so I think that was the same here. Yeah, so x sub n. Yeah, so my nth time step, the probability I end up at state j, is wholly encompassed by this matrix multiplication And that was a second year concept, so it's just a simple level. I don't really think it's too crazy. We usually define it this way. I'm glad that one thing that he did in these sets of notes is use this notation quite a lot, because it's such a pain in the ass writing all of this every single time. And p sub ij, that's okay, but we used to write stuff like this, and I thought that kind of looked ugly because I don't really think. I don't know, it looks like nth derivative, and this is just a better piece of notation. It looks like a function, and I think I just like function notation more. State I leads to state j is written as that. So this is just some stuff about communicating classes and how things talk to states talk to one another. But I think it's quite straightforward what it means to talk to someone. So if I do that entire diagram like shambolic mess all over again, like I did here. So I think there's a nice diagram on the other side that I can actually work off to show with this thing. State 2 talks to state 1 because there's an arrow pointing towards it with what's it called? A non-zero probability. I mean, you wouldn't draw this on and say probability 0, so I suppose I don't really need to say there's no arrow pointing towards it, but sorry, non-zero probability, but let's just assume, I'm going to assume simplicity here and say, yeah, you know what, you jump between two states if, a state talks to another one if there's an arrow pointing towards it. So that's good enough for us, in this case, being this is a recap and more of a criticism of the notes. So here, yes, 2 talks to 1 because there is a way of going from 2 to, there is an arrow directing from 2 to 1. So here it really says that probability of given that you've started at state I, you can end up at state j for some n in the future. So after some amount of time steps, you can end up talking to that. So yes, 2 does talk to 1 because there's a direct arrow pointing towards it. But similarly, 3 talks to 2 and 2 talks to 1. So that means 3 talks to 1. That's to say there is this 2-step route of getting to 1. 1 only talks to 1 and it talks to nothing else. 2 talks to 2 by itself, 2 talks to 3, 2 talks to 4. 4 only talks to itself, 3 talks to 3 talks to 3, 3 talks to 4. Really straightforward stuff. Nothing too crazy here. 3 also talks to 2, but I think I've already mentioned that one. So we could actually make this even more powerful by saying 2 things communicate if they talk to one another. So 1 only talks to itself, so it forms its own, so it only communicates to itself, okay? Because there's an arrow pointing out of 1 and there's an arrow pointing towards 1. Is that right? Yeah, that's right. Okay. 2 talks to 2, and well, yeah, that's obviously 2 communicates with 2, but 2 talks to 3 and 3 talks to 2. So 2 and 3 also communicate to one another. 3 talks to 3, so 3 communicates with 3. 3 talks to, well, okay, you could also say 3 talks to 2, 2 talks to 3, and therefore 3 communicates with 3. But it's just easier wrapping around this. 3 talks to 4, 4 talks only to 4, so 4 is its own munching of communicating. Own bunch of things that it communicates with. In fact, these bunches that we say only communicate with each other, we call them communicating classes. And the reason that is because this property of communicating is actually just an equivalence relation between states, and I think that's quite easy to say, easy to prove, because if I don't know, I talks to J, then if I communicates with J, like that, if I want to show that this is an equivalence relation, all I have to show is this. And so basically what I end up having to do is showing, okay, so this is the property that I'm trying to work with here. What I'm going to end up trying to show is transitivity, which is just saying if I talks to J, J talks to K, then I talks to K. But that's kind of obvious. For instance, if 3 talks to 2 and 2 talks to 1, right? Wait, what am I trying to do here? No, okay, I'm trying to say communicates. Yes, there we go. Slight mistake. Okay, I'm making a bit of a mess of this. Basically, what I end up having to show is two elements. Okay, the same elements have to communicate with themselves always. And that's trivially true because they are themselves. You could just say the 0th step, time step, when you're at that state. You could also say I communicate. Say I communicate I with J and J with K. Then I talks to J and J talks to K. So that means I talks to K. But since uh, K communicates with J, communicates with I, K can talk to J, J can talk to I, so K can talk to I somehow. You gotta imagine it as like a group of girls being really gossipy and trying to pass messages between each other. Okay, once again, if I talks to J and J talks to I, then I communicates with J, so J basically communicates with I too. I mean that's kind of obvious, right? It's like, yeah, these two people talk to each other. If I say, um, Joe and Mama talk to each other, right? And notice I'm using the word each other, so it's sort of implied that they're communicating. If Joe and your mama talks to each other, then your mama and Joe talks to each other. You don't need to really go crazy in explaining that. And well, this is a preliminary, so it's quite nice that they barely ever actually explain this. But I think maybe for some of the shitty, stupid viewers, I didn't say that. Someone else did. This would be quite useful. Okay, aperiodicity. Oh yeah, by the way, I stated this extremely intuitive, which is true. Um, aperiodicity. A state is periodic if the greatest common divisor is blah blah blah. Okay, basically what this means is, okay, there's no random weird way of being able to just jump back to yourself in a specific number of, no, in only a fixed number of ways of moving. And the way I once got taught this was thinking of a simple random walk. Um, so, for instance, in this case, say the probabilities are non-negative, then the only way to return to my state is either from going through two steps. You have to, okay, or 0 steps. I'm just here. 2 steps going from the next state and then back. Going 3 steps. So 2 steps going here, 2 steps going back. So 4 steps to return, and so on. So all the different ways of me being able to return are like this. This is the total number of steps that I need to take to return. And notice these are all multiples of 2. So what we say is there's not really periodicity here because it takes some fixed amount of time. I can like predict that it will take you only some amount of some sort of I don't want to say there's like some structure to how you're supposed to return to your original state all over again, as opposed for aperiodic states. If that just means that I'm not really sure how you might actually end up returning back to the state. You could end up returning in 3 states, 5 steps, 7 steps, 9 steps. There's no real like pattern towards them. Okay, well actually I just did multiples of 2 there, but yeah. So the idea is like even if you did something like that, like 3, 4, so 3, 5, 7, and 9 or something like that, there's still some structure towards it. What I mean more is like, I don't know, you could equally return as like, okay, no, the chances of these things happening might vary, but the fact that you can do them is equally possible, i.e., it's not a 0 probability. So something like returning back to the same state after 100 step is still possible, as well as just returning back in maybe 1 step is still possible. That's what we really mean by aperiodicity, and that's what sort of this greatest common divisor property thing does. This is kind of like a pain in the ass to explain when you're first trying to get into it, which is a bit of a shame because they hardly explain it, I think, in the notes from what I remember. Let's see. Do they give any explanation? No, they just say it. In fact, they deliver a nice little lemma afterwards. A chain is irreducible if and the chain is irreducible and at least one aperiodic state, then all states are aperiodic. And that's sort of to say that if you like, okay, irreducible just basically means every state can talk to one another. Okay, so it's one massive communicating class of states in a Markov chain. basically what you could end up doing is walking towards the really weird state, the one that you don't know how to return to. Do some amount of walk to that, and then try and return to that, and then in some random amount of steps, and then return to your original state. And then what you can basically conclude is, since you have no idea what kind of structure happens when you end up at the aperiodic state, um, you have no idea how, when you originally started, stay at like, okay, maybe this helps with a demonstration. Say 1 is my really weird aperiodic state, and 69 is some other state, right? Then what I need to do is some amount of like walk to end up going to 1. Say maybe, I don't know, maybe it takes 12 steps somehow to be able to get to 1. And then 1, basically, you need to wander around, but it's aperiodic, so you have no idea how many steps it might actually need to take to run back to 1. It could be any number of steps. And then maybe say it takes 24 steps to return. Then 12 plus some unknown amount plus 24 is still really unknown. Like, you have no idea. The point is, if you can go from... If 69 can end up talking to 1, and 1 talks to basically every state, for instance, then every one of those states can end up doing this sort of weird path towards 1, and then some random ass unknown amount of steps to really unguessable amount of steps to get back to 1. Then basically every state can kind of like be said to have no structure in how many steps it needs to take, because you could always fuck it up by walking towards 1 and trying to run back to 1. So I don't know. The lemma's pretty. What did I say about this lemma? Okay, it says just go from any state to the periodic one and we construct a funny walk. I mean, yeah, that's kind of what I mean by this sort of diagram here. It's not too complicated, but it would be nice if, because aperiodicity is not even well covered in second year. It's sort of just offhandedly explained and said to have some well-defined notion in number theory, but I don't know, you have to be sort of a math person to sort of get it, and I think that diagram sort of illustrate what I mean by aperiodicity just measures structure and how you're supposed to return to your original state, and irreducibility, which means everything communicates with each other, basically means if you can just walk to the one state that fucks everything up with structure and how many steps it takes to walk, and screws up your entire like mojo and trying to figure out how many steps it takes to return to your original state. Okay, hitting times is just some bullshit. Basically, it just means the first time until it takes to return to your original state. So that's at least h sub I. H sub I plus, that's like the first time since the original, since time being 0. So that is to say, first time. So it could be that you originally started, so x naught is equal to I. Say you might have originally just been at state I, then hi is going to be equal to 0 straight away. But hi plus basically says ignore the case on whatever happens when time is 0. When's the first time after the original time in which I end up ending up at state I? These were really fun to deal with in second year. They're not really touched too much on here. I think they have a little exercise near the end down here about asymmetric walks, which really nicely uses hitting times and all of that sort of stuff. But I didn't end up doing the exercise because I've done it to shit at this point, and I don't need to explain it to myself any more than I need to. So what are we doing here? Recurrence and transient states. So let I be a state, it's recurrent if the probability of returning in the future so not originally, is finite, has probability equal to 1. It's positive recurrent if there's that, and transient if that. These are all really straightforward things. Positive recurrence is probably just the most confusing part about this, and all that really means is, given that you started at state I, the chances of you returning is finite. So it's expected, no, not the expected, the expected returning time in the future is supposed to be finite. So I'm expecting to sort of return in less than finite, well, okay, in finite time, less than infinite time. So that's positive recurrent, and I think it's a bit stronger than this statement here. Um, what this statement really is saying is the chances of you ending up returning is guaranteed. Actually, is it stronger? No, okay, yeah, this is stronger, I think, because this is saying yes, I expect to return with 100% probability, because this is what that finite thing means here. So I'm saying that I will return in finite time, and it's transient if the chances of you um, returning in finite time in the future is not certain. So recurrent means you will hit state I again. Transient is like you might not hit it. There's like a chance that you might not hit it. Uh, so they don't really give any proofs for these sort of next statements because it's done in the previous course. In fact, yeah, this is why they're all preliminaries. It's really nicely stated. They just state what the definitions and theorems really are. In fact, they give this nice little uh, this nice little characterization of how to find all transient states and recurrent states down here and here, which was really nice to go over. I think there's nice, easy ways of remembering these things. So I wrote down, remember this by thinking, if the sum of the probabilities of eventually returning blows up, surely we should then eventually return. Anything else is a bit too weak. So that's kind of what this thing is saying. It's saying the chances of me returning is equal to 1. So I'm certain of me returning. If the chances of me possibly returning in some time in the future, so n equals 1 to infinity, blows up to infinity. So it seems to be like a strong enough statement to say, yes, the chances of the sum of all of the chances of me possibly returning just explodes. Like, it's just extremely, there's it just somehow manages to get me back to that state, but adding them all up, it's just too big. It's just too big, and anything less is just not enough. Okay, recurrence and transients for chains. If a chain is irreducible, will we say it's recurrent or transient? If all the states are recurrent or transient. So if a chain is irreducible, let me say, oh yes, that's to say, if everything talks to each other, then recurrence and transience is just a class property. Should have probably written that here, so let's just quickly do that real quick. I think it's this color here. Is this the right one? No, it isn't. Let's just use this for now. Oh, actually, maybe I can find out what color this is. Ooh. One sec, I'm gonna quickly pause this. Okie dokie, so I've put in the notes now on what I was trying to say earlier. So basically, where are we at again? Okay, so yes, recurrence and transients is a class property, and I think this is kind of obvious, and it sort of like falls out of the idea that, okay, so a chain is irreducible if every state talks to each other, i.e., it's all communicating, and we say it's recurrent or transient if all the states are recurrent or transient. It's a class property because if one of the states is recurrent and it's everything talks to it, then you can return to that state an infinite number of times and then go to every other state with non-zero probability. So it's sort of like, yes, if I can always return to at least one of these, I can always, with some chance, end up going to every other state, which should mean, in theory, that I should be able to, in infinite time, be able to return to every state an infinite number of times, because everything's talking to each other, right? Transients. Okay, let's see if we can do the same sort of argument with transients. If for whatever reason you're at one state and you can do a thing, you can end up walking away from that state and never returning to it ever again. If everything can talk to it, then you could just somehow, with non-zero probability, start at any point, walk all the way over to that transient state, and run all the way away forever with non-zero probability now. So it should be that there is a chance that you could just go from any point to and never return back to your original point. So it's sort of like saying, well, yeah, basically it literally just follows up that transience and recurrence is a class property. In fact, you get this nice little corollary: a chain on a finite irreducible state space is always recurrent. And why is this obvious? Well, if you're in an irreducible state space, everything talks to each other, and if it's finite, you're all sort of contained. You can't really drift away to infinity. So you sort of have to go from you sort of have to be able to jump between one state and every other state some infinite number of times, because it's sort of like saying, I'm going to flip heads and tails forever, and I'm never going to get tails. Well, the chances of you never getting tails is basically zero. And in fact, in infinite time, we literally mean that this will go to zero. This is exactly zero. In the same way, you can sort of envision a coin flip as like a finite Markov chain that's sort of like this. So it's like heads, tails, jumping between half and half. Now, you wouldn't tell me here that I wouldn't return to heads an infinite number of times, even though there's a chance that... Wait, is that true? No, okay, sorry. This is the correct. A half. Yeah, despite the fact that I can go from heads forever, you're telling me that I'm going to never hit tails. And my argument is, okay, well, at least this corollary says a chain on a finite irreducible state space is always recurrent, i.e. I should always be able to return to tails an infinite number of times too. So, yeah, get your mind out of the gutter if you're thinking that you can't do this. Silly. Okay, a row vector pi is invariant with respect to p if pi p equals pi. What this basically means is, the way I think about this is thinking about the actual lemma that I'm supposed to prove later on, which is the ergodic theorem, which is basically saying if the chain is ergodic, then your states sort of behave. You sort of behave in a how do I say this? In really far into the future. You're expected to sort of be at a specific point with respect to some sort of distribution. I.e., it's more likely that you're probably maybe you're equally likely to be at any state in the future, or you'll have some sort of bias towards being at state 1, maybe with probability 2/3, and states everything else with probability uniform as well. Or it could be that there's some sort of bias for every different state or something like that, in probability. So there's long-term behavior. We're expecting it to sort of be preserved in some sense. And what would that really mean? Well, that would mean that if I have some sort of non-negative, row vector where it sort of describes these biases as probabilities, then if I looked at one time step in the future, I should be at the same equilibrium distribution, i.e. if I did my row vector times my stochastic matrix, which tells me how I'm supposed to move one step into the future in certain probabilistic ideas, it should give me the same uniform equilibrium, i.e. pi p is equal to pi. So this does actually just fall out of its definition, and this is basically just literally the way you're supposed to expand out this this matrix multiplication. So it's quite straightforward, nothing too complicated. Just realized I think I didn't really explain this recurrence and transience dichotomy, but uh, I'm just going to. I don't know. I can't remember if I did it. I sort of like cut the video halfway through and realized, oh shit, I should probably explain all this stuff. So I'm just going to quickly explain it all over again. So it's a bit of a pain in the ass. I don't know if you could tell. I sound a bit different. I might have just forgotten what I talked about. But let's just assume that I've explained all of this stuff. If it doesn't make sense, it's sort of like, okay, well, you know, you know, uh, the chances of me returning to my state an infinite time is one. If the chances of me ever returning to it sums up to something, it just blows up. Like that sum blows up. Um, Whereas this one is saying if I don't really blow up with my probabilities of returning in some amount of time, then that's too weak. I have to like I need a stronger statement, and that is the one above. So it sort of characterizes if states are transient recurrent. So I mean that's boring. So let's just talk about something else now. Definition, detailed balance, and reversibility. So it was nice that they mentioned this because this came up. This was a quite of an important topic in last year's notes. I think it came nearly to the end of ST222. Yeah, I think it did. And it was quite. It was a bit of a pain in the ass because basically it talked about how if you sort of like let your Markov chain run, in the future, would you be able to tell whether or well, okay, in the future it would sort of behave like it's in this sort of equilibrium state. So as I mentioned, you might have some biases of probably being at state 1/2, state 1, state 2, state and so on, which is encompassed by your equilibrium distribution pi. If you let it run from there on, you should expect that in one time step, you should have the same sort of equilibrium distribution. But in the same sense, if you're at infinite time, one step backwards should give you the same sort of distribution. That's what we mean by reversibility. It means that if you sort of run your Markov chain off, surely it should be that it's reversible if you can't tell if the Markov chain is running forward in time or backwards in time. So we encompass this in this idea where we have some sort of equilibrium distribution, and we say, imagine I'm at equilibrium distribution at state I, so the chances of me being there. Then if I jump towards J, it should be indistinguishable to if I started at J in equilibrium and jumped to I. So detailed balance is just an encompassing way of understanding time-reversed chains, which is basically what the next theorem says. Suppose pi and p satisfies detailed balance, then if you let it run, if you let it run backwards, it's the same Markov chain with the same stochastic matrix P and initial distribution. So yeah, it's exactly the same thing. He gives this like nice little exercise about what are they called? Simple asymmetric random walks. But I've done these to shit, and I can't be bothered to explain them any more than I already understand them. He does mention a little bit about minimal solutions, which is more of a theoretic result, which helps you to show these how long-term behaviors irreducibility in long-term behaviors are supposed to be understood, because usually these things go by, hey, look at this thing, does this. So actually he states it here: show that the chain is irreducible, show that it's periodic, show that it's transient recurrent. The transience and recurrence relation relate to whether or not you sort of like solve this, some sort of system of, what are they called, recurrence relations, and it's a bit of a bitch, it's supposed to be, what was it again? No, it's not like a recurrence relation. You like invent the system of equations, and it's sort of like the minimal solution to these systems of equations, which is exactly what they do here. They come up with these annoying invariant things that should happen in long term, and honestly I kind of find them lame, and I've done them for so long they're not really worth talking about. So I'm just going to talk about the next section, which is kind of interesting. It's the continuityification of the discrete area, which is what we did before. But one thing I don't like is that all of the definitions basically are the exact same. Like, look at this. This is a T here, and look what he does in the first page. So let's go to page number 1. 1. Move. Okay, maybe not page number 1, but here it's just an N. So it's a bit of a pain in the ass to read these things because you have to do it all over again. And all that happens is you realize, yeah, well, I've got a T here now, you know. Rather than having discrete time steps, I actually have to care about how much time happens in between each time I jump to a new state. But it's fine because they're so simple, they just kind of read off the exact same way. So here you can read off time homogeneity in the same way. So remember how I mentioned um, time homogeneity sort of really only means the difference in time steps is all that matters. Here it literally means the difference in time is the only thing that matters. So if I'm at time s at state I, then what's the chances of me jumping to state j at time t is the same thing as just knowing how do I get from state I, and say I start at state I initially and I jump to state j in t minus s time. Well, then hopefully those probabilities stay the same. So it doesn't really matter how much time actually happened um, between jumping. It's no, it well, yeah. The only thing that matters is the time between jumping, rather than the time where you initially started. So it's time homogeneous to its name. Okay. Then there's these nice little simplest continuous time constructions, which is really basic. It's sort of like saying, yeah, take a discrete time Markov chain and randomly sample some times that are exponentially distributed, and set your continuous time Markov chain to be basically the exact same Markov chain, except you just sort of like vary the times because you don't really have time steps anymore. You have times until you first jump, which is what these holding times and stopping times are. And they all have the same exponential 1 distribution, but one of the most annoying things about these notes is that they kind of shittily explain why the exponential distribution is so useful until like later. So I didn't mention here, yes, the exponential is the only continuous distribution with the memoryless property. Okay, but it's the only one on zero infinity with the memoryless property. I don't know if there's some mumbo jumbo bullshit, but we use exponential 1. Well, he always uses exponential 1 because it's really easy to jump between. Okay, sorry, let me just do this again. Yeah, so exponential. Yeah, it's really easy to jump between exponential 1 and exponential lambda because of this property. So I gave a little bit of an explanation because he didn't do it in his notes. If t is exponential 1 and s is exponential lambda, then these two probabilities are related like this. So it's very easy to convert between exponential 1 random variables and exponential s random variables just through this little rescaling of parameter of your event in a probability space. So there's that. Vertex rate constructions are sort of like the exact same thing as before, except you're sort of you're trying to jump between you're trying to jump to the next state with maybe less than maybe with different rates. So rather than having your times be dictated by some exponential random parameter where the parameter stays fixed, your time is exponential but varying with a different rate. Yeah, so that's not too complicated. I don't really care for the vertex rate construction. I care more about actually the next sort of stuff that he mentions. So is there anything else that's interesting here that we should talk about? Probably not. Yeah, so edge rate construction is quite interesting because it's sort of like saying start at I don't know, maybe you initialized at state I at time t greater than or equal to 0. Then what you basically want to do is randomly start sampling times for jumping between them, and the first time, okay, the smallest time, i.e. the first time when you can jump, you jump to that state. So here we say t sub j is exponential qij, where qij is supposed to be the rate from which you jump between I to j, and you take the minimum of those times. So it's like the first time that you can actually be available to jump to some j. and whichever state that is, that's going to be the argument of this thing. So that's that state. So basically, you just end up staying at your original state until the first time that you can jump, you do jump. The way I like thinking about this is like, you have some crazy amount of ADHD and you're trying to jump between states or something like that, and you're like, you know what, whichever one, okay, for every single other states that I can jump to right now, do me a favor and just randomly like flip coins or whatever to determine times. And I don't know, maybe these coins are exponentially distributed with some sort of parameters, some sort of rate parameters. But whichever one gives me the smallest time that I can start running to the next state, I'm going to go to whatever state that is. And that's basically what the edge weight construction is. It's just some hyper guy waiting for this first opportunity to jump to a state and takes it. So it's easy as that. Yeah, so I'm not sure really what he says about it. There's a lot of talk about how the exponential distribution is sort of like a Bernoulli, sort of behaves like it's Bernoulli in small time intervals, which is one of the nice properties about the exponential distribution. But the fact that it's explained so shortly is kind of disappointing, especially since there's a lot of deepness to the exponential distribution. For instance, being very nicely related to the geometric distribution, but more of a continuous version of that. So, I mean, whatever. We give some large standing assumptions, and we talk a lot about how the rates of jumping is sort of like the first derivative of the transition matrix, which is kind of cute, but it spits out of this lemma about competition of exponentials, which doesn't really have any explanation until they leave it to you basically as an exercise, which I have actually proven, which I have done, but it's a bit annoying if they leave it as an exercise for much later and uses it as a property currently. So maybe the notes aren't very well written in that regards, but which sort of happens on this page down here. You notice how they talk about this lemma here, and then they don't give any sort of like explanation, but they do give this sort of idea as to why I need it, and then 10 pages down the line they ask for it as a lemma. So yeah, that's all the edge weight construction stuff, which isn't too crazy. There's some talk about how it relates to infinitesimals, but infinitesimals have their own sort of analysis that you do in this module, so I suppose I'm just going to ignore that. Stopping times are defined exactly the same way. Strong Markov properties defined exactly the same way, sort of just depending on stopping times all over again. What else is there? Okay. Chapman-Kolmogorov, holding times, jump times. Yeah, so... wait, no, that's not what I want to do here. Okay, Chapman-Kolmogorov equations. That's literally just like a matrix multiplication. So we define these transition matrices, but depending on time, as to be like P of t, right? To be the transition matrix at time t. And if you assume all these nice properties like Markov property, time homogeneity, then you end up getting this lovely little theorem that says P of s plus t is equal to P of s times P of t. And that literally just spits out the definition and time homogeneity and all of that. I think at one point or another they say that you need to use Bayes' theorem, but I observed that it's just this property that you need to derive, and I don't see how that's exactly Bayes' theorem. Bayes' theorem doesn't say, hey, given this event, no, you can't just say it's Bayes' theorem every single time you have probability of something happening given something happening. Okay, it's not always Bayes' theorem that you need to use. Bayes' theorem is just a specific rearrangement of that of that statement, and it's not the statement that I've written down. So, whatever. I thought the proof was really straightforward, so I didn't really give it too much thought. Standing assumption 2 was that you get uniform continuity, and it just says all of these P of T's form a semigroup of stochastic matrices. So P of 0 is supposed to be equal to I, because what it basically is saying is the diagonal is supposed to be 1s and 0s everywhere else. And the diagonals being equal to 1 basically means probability of going to state I at time 0, given that you started at state I. I mean, what would you expect that to mean? So you start at, you know that you start at I at time equals 0. It is time equals 0. What's the chances of you being at I? Should be 1. That would be what the diagonals basically say. Okay, which is why the diagonals 1. If I said the time is equal to 0, given that you start at time 0, given that at time 0 you start at I, what's the chances of you being at a different state, j? You would tell me, obviously 0, right? Well, that would be basically every other entry in the matrix of p of 0. So p of 0 should be equal to I. P of t plus s is just equaling p of t times p of s is just Chapman-Kolmogorov equations, which is something you really hope to have because they're extremely useful. And p of ij of t being greater than or equal to 0 and having row sum equal 1 is just us trying to preserve the same property as having row sum equals 1 in the discrete case. So it's literally just the continuousness of the discrete case, which was really nice and lovely, and we understood before, right? We all understood it? Yes. Okay, great. So moving on, yeah, you get this. Okay, well, maybe I'll talk about the other stuff here. Yeah, so they give this standing assumption 3, which is like, yo, wait, did I write it down? I don't know if I wrote it down. Whatever, I suppose we could just talk about this theorem 1.2.5. Standing assumption 3 just means that you can be a Markov chain and it's right continuous, which basically means if you given any like time on your Markov chain, I should be able to move a little bit forward in time and I'm still at the same state I was before. So yeah, that's really what's it called, right continuous means for a Markov chain. Anyways, moving on. They give this theorem which is sort of like saying you can encapsulate all of the idea of the you can encapsulate all of this idea of your continuous time Markov chain just by giving your transition matrices and your initial distribution of x0, and that basically follows exactly from the same idea as when you did discrete time Markov chains, which you literally define by its initial distribution and its transition matrices. So it's nice that there's a little theorem for that, even though I would have thought it would be part of the definition, but it seems as if you kind of need to characterize it some way. I don't know. Whatever. They only give the proof sketch, but I'm assuming it's because it's complicated and boring and measure theory related, so I kind of just ignore it because it's not really examinable. They gave these nice 2 little exercises which solve really quite easily. I mean, here's my solutions. If you want to show that something's a semigroup, you just check these properties here, which we defined earlier. And, well, you know, the first one is obvious. I can show that its transition matrices look kind of like this just by definition. And I can show it's not a semigroup by looking at its bottom left entry. It's this one here. So p of t plus s is supposed to be equal to this thing. But when you do p of t times p of s and you look at its bottom left entry, you end up getting this ugly s object, which is clearly not the same thing. The next exercise is really straightforward. All you have to, by the way, if you want to be able to actually derive this, all you need to do is realize that this is the 0,0th entry, and that's the 1,1 entry. So that's 0,0 here, 1,1 there, and row sum is equal to 1. So you just do 1 minus everything, which explains this line here. So I thought it was a really straightforward problem. Just gets you to remember that row sums are supposed to be equal to 1 for these transition matrices. And exercise 1.2.7 is basically saying, check that this is, just verify that this is a semigroup. So all you have to do is check these 3 properties here, which is really easy, except for except for this property, because everybody knows that all of these things have to hold. Okay, I mean, it's just easy. Just plug in p of 0 and realize everything here is non-negative, and the row sums are equal to 1. Easy peasy. But p of t times p of s requires a bit of algebraic manipulation to actually show it's equal to p of t plus s. Given my working out here, it's quite straightforward. You just have to actually do the matrix multiplication, and yeah, you get it verified. So yeah, I mean, that's the first 20 pages of the notes. I think I'll give a more thorough examination of the rest of the notes maybe some other time, because it's now getting to half 12 and I want to go sleep. Alright, you got any crazy ass questions, I suppose you could just put them in the comments. This has been my sort of analysis on these notes, where I've been sort of thinking about what it actually all means. We got through 20 pages today. I suppose we could go through maybe about 20 pages tomorrow, and maybe in like 5 days we've had covered all of the notes. So I don't know, what are my thoughts on all of these notes? I think the preliminaries were easy enough and really straightforward, but a bit of a pain in the ass to have to rewrite basically the exact same definitions twice. Um, and some of the stating some random properties about, say, exponential distributions without even first defining exponential distributions, some of its original properties, and some of the defining properties that we really want to use later on in the term, only giving sort of infinitesimal understandings of them. Bit of a pain in the bum, but you can work with it. You can live with it. I mean, I managed to break through, give some reasonable analysis, and I think if you look through my notes maybe carefully on YouTube, pausing at each step, maybe it'll make more sense to you. If there's any mistakes in my notes or in their notes, actually, I'd be happy to see them, because it helps with my understanding too. So yeah, I've given a bit of my rewrites and my solutions and my understandings here. So I don't know. That's my take on this thing. So Zooey Mama, and take care, I suppose. Catch you around.